This is the second part of solving differential boundary value problems using Matlab function BVP for C. So in this video we're going to look at the second example where the problem is finding the concentration distribution in a cylindrical coordinate. We have the diffusion of a species with concentration variable C, and we have the diffusion coefficient D times the basically diffusion in cylindrical coordinate. This is D squared C dr squared plus 1 over R d C dr minus, this is some source term or maybe the reaction term. So something is produced, and then something, well, the same thing is produced is going to be diffused. And the diffusion is equal to production. That's how much we produce is going to diffuse. And these are exactly equal because mass is not produced, or mass is conserved. Alright, so with some known boundary values, so the concentration at the end or at the periphery or at the surface of the cylinder is 1. The radius of the cylinder is 0.002. Diffusivity is 0.007. Because of the symmetry, we know that the derivative of the concentration, which is the flux, is 0 at R equals 0. Which means the concentration should not have any slope, or there is no flux at the center of the cylinder because it's axisymmetric. So anywhere you look at, it should be identical from the center. That's why the slope of the concentration at R equals 0 is 0. Alright, so as you know, in Matlab or any boundary value solver, we need to convert, other than direct method, we have to convert higher order differential equations to first order system. So we need to convert the second order differential equation to a first order system, and to do that the technique is the unknown is going to be the first unknown, which is the concentration. The second unknown would be the derivative of the first unknown. So if C is the first unknown, derivative of that with respect to R is the second unknown. I put these two in a vector. So now I have C and D, C, D, R. These two will be my unknown list. Then I look at derivative of this vector with respect to R. The first one is D, C, D, R, which is by definition just D, C, D, R. So we don't have any new information in here. So we just write D, C, D, R as 0 times C, which is 0, plus 1 times D, C, D, R, which is D, C, D, R. So this row times that is going to be D, C, D, R. The second one is ddr of dcdr, and that is the second derivative of C with respect to R, which is equal to, if you use this equation, is going to be, you can divide through by d, and then you find or solve for d squared cd dr squared, which is now equal to negative d over r. So this term goes to the right side. You divide by d, so you get 1 over dr dcdr, and that is I'm sorry, we're going to divide by d, then this term goes to the right side, so then you get 1 over r dcdr, so that's 1 over r dcdr with a negative sign because it goes to the right side, and then plus kc squared divided by d, and that's kc squared divided by d. You can also write the second equation this as the second line of this matrix multiplication. So if I multiply this row by that column, you get the second equation here. Alright, so now if you see, I have ddr of some vector, let's call it y, is equal to something times, again, y. And that is the first order differential equation. dy dr is equal to something times y, and that is exactly first order. So now I can go ahead and solve this using BVP for C in Matlab. So I'm going to switch over to Matlab and show you how we can do this. So here is the setup. We put the constants in here, diffusivity, and maybe reaction constant, domain length, which was 0.002, number of discretization point, I have, let's say, 100, and the tolerance for convergence in MATLAB is, I just put 10 minus 5, and to plot the concentration from, let's say, along the diameter of the cylinder, then I look at a vector called, let's say, x vector, and I need to plot the function from negative r to r or negative l to l on that vector, or on that axis. So then that means I'm looking at the concentration along the diagonal. If 0 is the center of the cylinder, then negative L is going to be on one side or left side of the diagonal, or the diameter, and then L is going to be the right side of the diameter. So I'm basically looking at end to end of a diameter and see how concentration changes over the diameter of a cylinder. Alright, so as you know, we have to create some initial guess for the unknown, which is the concentration and the derivative of it, if you remember. Our unknowns are the concentration and derivative of that, or the flux. So I have to make an initial guess for that. So let's see how, right here, how that function actually implemented. So let's go there. So what I'm saying here is, if I'm looking at the left half of the diameter, which is r less than 0, then I put concentration equal 0.5, like fixed concentration. And for the right half of the diameter, I put 125. Alright, so this is just a guess. So like two constant values. Below 0, I have 0.5. Above 0, I have 125. Alright, so right. So I'm going to go back, and now I have my initial guess. Then we call BVP for C the function first. And the way to write the function is exactly we write this vector. So the first element of it is dCdr, which is the second element of my unknown vector y. So that means the first element of this dy dx is going to be the second element of the c vector, or the y vector. Then the second element of dy dx is going to be this thing, which is negative 1 over r, and this thing is the second element of my unknown vector. So it's right here, minus 1 over r times the second element of unknown vector c, and then plus k over d times the first element of unknown vector raised to the second power. And that's what I have here, plus k over d times the first element of unknown vector, which is c here, raised to the second power. Alright, so now here is just to make the function smoother. If r is less than 10 minus 10, which is almost 0 in MATLAB, we assume, well, r is very, very small. You don't want to put a very small r in here, because that is going to blow up. It is 1 over r in there. So to avoid that, we're going to kill this term, because we know that when r is 0, perhaps concentration might be 0 too, and this 0 divided by 0 is maybe a number, but we don't know what this, I'm sorry, this is the derivative. The second element of c is the derivative of c with respect to r, and we know that at the center this thing is going to be 0 divided by 0. And because we don't know it, we have to find a limit for it. And the limit for this thing is going to be 1/2. Right, so this plus that, when r goes to 0, is going to be 1/2 of this squared times 1 over dA. Right, so if you're very close to the center of the cylinder, then this is going to be my dy dx. With the first term is as before, the second term is modified if r is very close to 0. If you don't do this correction, then when r goes to 0, then you get 0 divided by 0, and it's not a defined limit. Okay, so that is the function. The second thing we need to see is the boundary condition. We said this needs to be written in a residual form. So the boundary condition is, remember, the concentration has to be 1 at the, let's look at the boundary condition here. So the concentration should be 1 at the surface of the cylinder. And regardless of where we look at, either the right side of the diameter or the left side of the diameter, it has to be 1 because it's always on the surface of the cylinder. And that's exactly what it's saying. So we have the concentration on the left end of a diameter, the concentration on the right end of a diameter. And both have to be equal to 1. So the residual would be the error I make by having a solution Ca on the left side of the diameter compared to 1. So this is the error I make between the solution I calculate and the exact value I have to make on the left boundary. On the right boundary or right side of the diameter, again it's 1, so the solution I get minus 1 is going to be the error I make. And these two elements give me the error I make on the boundary. So this turns out to be the residual of the boundary conditions. And I put that in the second argument. The third one is the initial solution that I guessed. And then the fourth element here, or the fourth argument, is the option for the tolerance. I divide my domain from minus L to L with 100 elements. Then after I solve the problem, I evaluate my solution or interpolate my solution at these given discretized points. Then I get C eval, and so remember C eval has two things in it, the slope, which is dc dx, and the concentration. So I first plot the concentration, which is the first element or the first row of C eval, this vector. This has the concentration, and the second row of this vector or this matrix is the derivative of it. So I'm going to plot both of them on one figure. If I run it, then there you go. So this is the concentration, the first element of my unknown vector, and the axis for it is the blue on the left. This is the derivative of it. It's red, corresponds to the red vertical axis on the right. Again, slope here is very negative, and that's why we have a negative slope. Well, that is about minus 800. That's the flux. And then the slope here at the center is it gets to some positive, or still, I'm sorry, this is still negative, so it gets to the slope, the slope here is 0, and the red line shows the slope exactly equal to 0. Then the slope goes up toward the end, which is about 800. So if you look at the red, it says 800, this is the slope of the blue. Alright, so the red again is the derivative of the blue line. This is the equation we're solving. We're looking at a diameter from the left of the diameter to the right of the diameter. This is the center of the cylinder. So the concentration is high on the surface, which is exactly 1. We're satisfying the boundary condition. And then the derivative at the center is 0, which was another boundary condition, if you remember. So the flux is 0 at r equals 0, and then the concentration is 1 on the surface. So hopefully this shows you how to solve boundary value problems using BVP4C in Matlab. Just to let you know that this can be only applied to one-dimensional problem. So that you can have only one independent variable x. You cannot have x and y. So if you have two independent variable, like two spatial coordinates, you cannot use BVP4C. Alright, so hope this is useful, and thanks a lot for watching.